Okay, so today I'm going to talk about igneous rocks, and I'll talk about the kinds that we see in the UK in particular. I'll look at the chemistry, how they form, and then how the chemistry of them affects their occurrence as both extrusive igneous rocks and intrusive igneous rocks. So it should provide you with a framework for understanding what you're looking at when you see granites or basalts or andesites in the field. Okay, so let's start off with the chemistry of igneous rocks. This is a really useful chart. So we have the volume percentage of minerals on the vertical axis. So they add up to 100%. If you have a rock, it's made of something, so it adds up to 100% of something. And then along the horizontal axis, this is the amount of silica in weight percent in the rock in total, so the bulk chemistry of the rock. So on the left we have 70% silica, very high silica rich rocks, things like granites. And on the right we have things down at 40% silica, very low, and these are peridotites. And actually when you're down at 40% silica, you've got pure olivine. So these are very basic rocks. At the top, we have the names of the different rock types. The lower names are the intrusive ones. So these are what you get when the magma doesn't reach the Earth's surface and it cools very slowly and produces what's called a plutonic rock, which is very coarse-grained. So granites are a good example, or gabbros are a nice example of a basic, intrusive, coarse-grained basic rock. And then above that, these top ones, rhyolite, dacite, andesite, basalt, these are the fine-grained extrusive versions. So when something is erupted onto the Earth's surface, it cools very quickly, so there isn't a lot of time for crystal growth, so you get a much finer grained material. So these are the intrusive and their extrusive equivalents at the top here. So if we look at the kinds of rocks that you might find in the Earth, first of all, we have these things between about 65 and 70% silica. And these are granites. So granites and granodiorites, these kind of 70 to 60 weight percent silica, these are what make up most of the continents. They're very rich in silica, which means they're light, they're low density, which is why the continents end up floating on top of the mantle. And it's also why you end up with thicker continents, and the continental average altitude being higher than the oceanic average altitude. It's why they're the land masses, because this stuff is less dense, so it floats shallower in the mantle, rather like icebergs floating. So that's the continental crust. At the other end, down here, these basaltic compositions, 50% silica or so, relatively basic, relatively low in silica, so we call it basic. This is what oceanic crust is made of. This is what you get if you melt the mantle. Okay, these compositions here. In between, we have things which are intermediate between these basaltic compositions and the granitic compositions. These are andesites, and normally they're produced where you have interaction between basaltic melts and the continental crust. So they're interactions between the mantle and the continental crust. So typically you get them above subduction zones where you've got partial melting of the mantle, which produces basalts, which then those basalts then interact with the overlying continental crust. So a good example of a place where andesite is currently being produced is the Andes, as the name might suggest, and that's sitting above the subduction zone of the Pacific Ocean, where you're producing melt, which is impinging underneath the South American plate and interacting with the continental crust and making these andesitic compositions. So you make andesite by mixing between granites and basalts. Okay. And then finally we have peridotites, and peridotite normally you don't see at the Earth's surface. This is what the mantle is made of. Occasionally you can make it by cumulate, by crystal settling from gabbroic basaltic magma chambers. So you see it in places like the very core of the Cuilin complex in Skye. But generally we don't see these on the Earth's surface. Okay, so that's a summary of the different rock types. So how do we read this chart beyond that? So what we have is we have the volume percent of minerals along this vertical axis. So if we consider a granite, a granite has about 50% of feldspar, orthoclase feldspar. This is the pink crystal that you get in granites, is a potassium orthoclase feldspar. Okay. Then we have from 50 to 30, so 20%, 20 volume percent quartz. Sometimes you get maybe 10% of another feldspar, plagioclase feldspar. This will be the sodium-rich feldspar. And then a few 5 to 10% of micas. Muscovite is the white mica and biotite is the black mica. And sometimes a little bit less than 10% of an amphibole. So basically you sum up over here, and that gives you the volume percentages of the different minerals which make up the rock. So that's a granite. A basalt down at the other end has feldspar, plagioclase feldspar, up to about 30 or 40 volume percent. It's dominated by pyroxene, and typically two pyroxenes. So there's a calcium pyroxene and a magnesium pyroxene, which make up this pyroxene volume. Then sometimes you might get a little bit of accessory olivine as well, so maybe 5 or 10% olivine. So that's what you get in a gabbro. In between here, in these andesites, you can see things are very rich in feldspar, and then rather than pyroxene, the pyroxene component, which is what's taken the magnesium and the iron in particular, you get instead amphiboles, and the biotite mica, black mica, becomes quite significant as well in andesites. Okay, so that's how you read this chart. It's a very useful chart to have at your fingertips, because it describes the rock types, what you're going to expect to find in the different rock types, and how they vary as a function of the chemistry. Okay, so let's now let's have a look at the rock types, see what they look like, and then we'll talk about how the chemistry, in particular the silica content and the water content, affects the physical properties of the magmas. So this is a granite up in the top left here. There's a very, very large orthoclase feldspar crystal here, this thing here. It's got some zonation in it, so you can see it grew and overgrew and trapped different things as it grew. And the little dark specks in here, and the dark specks through here, are probably mainly biotite mica. Okay, so that's the mica, these little black specks. The white and the pink are both orthoclase feldspar. And then this slightly yellowy, vitreous looking stuff here, through here, these are the quartz crystals. And so you can see it's mainly feldspar, quartz, and then very minor amounts of mica. Okay, so that's a granite. This is a gabbro. The feldspar in the gabbro are these white rectangular or needle-like crystals. So they're the feldspars. These darker crystals that you can see are growing around the feldspar and are the largest crystals. These are the pyroxenes. And then in this one, this has some olivine in it, and the olivine is weathering it's releasing iron oxide as it weathers, so it's making the rust colour. So these brown spots here, and here, these are olivines, which are weathering to produce this brown spots. And this is quite common. If you have an olivine-rich rock, you often get this brown, spotty appearance to it. Okay, so there are granite and gabbro in hand specimen. In the field, they look like this. This is Cuilin snecta, which is basically granite, and it's very pale. Because it's very high in silica, the feldspar and the quartz are both colourless minerals, or very pale minerals, so they dominate the coloration. Whereas here we have in Ardnamurchan, we have gabbro, and that's dominated by the dark minerals. And in fact, when it's very fresh, plagioclase feldspar is a dark colour as well, it's dark purple. So we have darks, dark greens, dark browns, dark reds from the olivine and the pyroxenes, and a dark purple colour from the plagioclase feldspar. So you get a dark colour in basaltic rocks and their coarse grain equivalents. So to summarise, granite and rhyolites contain about 78% silica, and they have up to 8% water in them as well. That's a lot of water. That's like 1 in 4 of the atoms are being replaced by by hydrogen or oxygen associated with water. So that's a lot of water. Gabbros and basalt at the other end, they only contain about 50 weight% silica, and they typically have less than about 1 weight% water in them. And then intermediate between those, we have the andesitic suite. So the intrusive is diorite, extrusive is andesite, and they contain about 60 weight% silica. And the silica content in particular really affects the physical properties. So you would expect andesite to be intermediate in terms of its properties between granite and gabbro. So I'm going to talk about the granites and gabbros as the end members for the kinds of properties and behaviours you might see in the field. So this is a crystal structure of quartz. So silica, SiO2. The grey atoms in this model are the silicon atoms, Si4 plus ions, and the red ones are O2 minus. So you have SiO2 makes the charge balancing correct, and for every silicon there are 2 oxygens. So this silicon is surrounded by 4 oxygens, and then these oxygens each bond onto 2 silica. So you end up with this 2-to-1 ratio of the number of silicon is half the number of oxygens. Okay, and all of the silica are sharing 4 oxygens, and all of the oxygens are sharing 2 silica. Okay, so we can draw a little shape around the oxygens around this silicon like this, so a tetrahedron. Okay, so the silicon is called tetrahedrally coordinated with these 4 oxygens. And you can, if I were to draw all of these tetrahedra, it's a good way to see the network. You can see that they're all corner sharing, and you end up with this extended network where all of the silica are sharing corners with 4 other silica. If you compare that to enstatite, so enstatite is MgSiO3, so only half of the cations are silica cations and the other half are magnesium cations, which are drawn in these blue octahedra here. You can see that the silica tetrahedra form corner-sharing chains, but they only connect in one direction. In the direction this way, they're isolated, and also out of the plane of the screen, they're also isolated. So they're only corner-sharing in one direction. So as you go from more silica-rich, you go from something which is very corner-sharing, everything is corner-sharing the tetrahedra, to something which is less corner-sharing. In fact, when you get to olivine, then you just have isolated SiO4 units surrounded by magnesium polyhedra. So if we convert that into what we know about the melts, this is a model of amorphous SiO2, so a molten structure of SiO2. And you can see again the silica tetrahedra sitting here, and they're corner sharing again in all of their corners. So this is going to be a very highly polymerized melt. It'll behave a little bit like spaghetti in that all of those polymers will tangle up. So it must be very, very viscous. It's hard to shear that because they're going to tangle all of these long chains. If we look at an enstatite melt here, top right, you can see that some of the polyhedra, some of the tetrahedra are sharing corners here. There's one that's sharing a corner back here as well. So there is some corner sharing, so some polymerization, but not very much. And then this is actually an olivine melt. You can see it's dominated by isolated SiO4 units. So there's no polymerization at all in the olivine melt. So if you try and shear this, there's no tangling going on. This is going to be a very low viscosity. So we should see a difference in viscosity from the silica-dominated chains in very acidic, silica-rich magmas to isolated things which are very low viscosity in basaltic and peridotitic magmas. So this is a plot of viscosity, log viscosity. So every time it goes up by 1 here, the viscosity goes up by a factor of 10, okay, by 1 order of magnitude, against water content, and plotted for different temperatures. So as you go to higher temperature, this is 800 degrees C here, this is 1000 degrees C here, this is 1200 and 1400 degrees C down here. So these are for granitic melts. So these things with 70 weight% silica in them. Basalt is down here at 1200 degrees C. Basalt has a viscosity of about 10 to 100 Pascal seconds. So it's down here somewhere, about where it says A of albite. So a granite with the same water content is up here at 10 to the 11 or 10 to the 12 Pascal seconds. That's 1 billion times more viscous. To put that in context, this 10 to the 2 Pascal seconds, this is about 10,000 times more viscous than water, and it's actually about the same as tomato ketchup. So down here we have tomato ketchup, down here we have water, and then all the way up here we have granite, so it's massively more viscous. There is a temperature effect, and typically for magmas, for granitic magmas in the Earth's crust, they're typically at about 650 to 800 degrees C, so somewhere up here. Okay, water contents up to say 2 to 6% water, so it's going to be somewhere up here. So these are the basalts down here. Granites in the crust are up here. Okay, so really much higher viscosity. So that's going to affect the way that they move through the crust. If you're so high viscosity, then you're going to need much larger forces to allow you to move through the crust, to flow in the crust. So the movement of magma in the crust is driven essentially by density differences. Magma is hot, it's a liquid, and so it's low density. There's normally an increase in volume on melting. Ice is unusual. Water is unusual in that the solid floats. Most materials, the solid sinks, and the liquid has a much larger volume, typically 4% increase in volume on melting. So this volume difference, this density difference where the magma is less dense than the crust, means that magma wants to move up through the crust, and that's why we get eruptions. That's why stuff comes up. So if we now look at typical intrusive magma bodies for granites and for basalts, you can see that they're very strongly controlled by the viscosity. So over here on the left, this is on Ben Nevis in the Cairngorms, and the Cairngorm Pluton, so this is a granitic magma body, basically runs to the edge of that U-shaped valley, runs through here. So everything that we can see here, and for several kilometres behind the camera person as well, that's all one granite body. So they're tens of kilometres long, kilometres deep, hundreds or thousands of cubic kilometres of material in one of these granitic plutons. Okay, so very large magma bodies are required to drive the flow in the granite and allow it to flow through the crust. Okay, on the right here, this is a basaltic magma body just here. It's a dyke. You can see that it's only maybe less than 1 meter thick. Okay, it's parallel sided and very straight, so it's gone through following the tectonic stresses of the region. And this dyke here is on the Bealach Nabar, and you can trace it all the way through to Skye. So this has moved tens of kilometres on a crack and flowed tens of kilometres on a crack which is only barely 1 meter thick. Okay, so much easier to flow. Okay, so that's why you get these very different styles of intrusion from these very large granitic bodies, if you think of the Cairngorms or southwest England, and these very narrow dykes and sills that are typical of basaltic bodies. And we see similar differences in the eruptive styles as well. So this is what you get when a dyke reaches the Earth's surface. This is in Iceland, and this is a basaltic dyke, and you can see it's called a fissure eruption because there's this fissure, this crack through the crust. That's basically where the dyke has been propagating up through the crust. It's reached the Earth's surface, and so it's now not confined, it's just flowing out horizontally over the surface. So this is typical for basaltic eruptions. Not massive explosions, some fire founting as it's degassing. You can see the gas is getting out quite easily, and then it flows because it's low viscosity. So you get these very low angle lava flows which aren't very thick. They can get to maybe 100 or hundreds of meters thick if you have enough magma being erupted at the same time, and maybe if it's partially crystallizing, because crystals will increase the viscosity. But typically they flow a long way and they're not that thick. So they end up producing volcanoes with very low angles of slopes on them, shield volcanoes. By contrast, this is what you get when you have granitic rock erupting. In fact, this is a dacite. This is Mount St Helens, the Mount St Helens eruption from the mid-1980s. And here, this is rather like a granite composition. And what was happening is that material was filling up the magma chamber, which was causing the magma chamber to inflate. So the ground above the magma chamber was getting steeper as everything was filling up, and eventually one side of Mount St Helens became unstable. There was a landslide which decompressed the magma chamber, and rather than all the gas escaping as a fire fountain, because the viscosity is so high, the gas can't escape, it's trapped within the magma. So when you lift off the lid of the pressure cooker, as it were, that gas boils, and there's a massive volume expansion. It's still trapped within the magma, so that then basically fragments the magma and turns it into a major explosive eruption. So these are the kinds of things that you get around the Ring of Fire. These big explosive eruptions. This wasn't particularly big. It was devastating over a wide area, but this is really quite small for the kinds of things that you can get. It wasn't a Caldera collapse kind of eruption. So what we see in the UK are Caldera type eruptions. So these are even bigger. The magma chamber is maybe slightly deeper than it was at Mount St Helens. Once again, it fills up, you start to get some kind of overpressuring, maybe as it's crystallizing, and all of these very high contents of fluids, as it crystallizes, they get exsolved, but they can't escape from the magma, so they make bubbles, which get overpressurized. Maybe it's the pressure of those that finally disrupts the land above it and causes these big caldera collapse eruptions. So this is the kind of deposit that you get after one of those big eruptions. Ash is thrown up high into the atmosphere and it blankets everything. So this is Fish Canyon in the States, and you can see that the ash landed. It was probably relatively cool. It didn't weld, so it's made this rather easy to weather material. But you can see it's covering everything, hundreds of meters thick, covering tens of square or hundreds of square kilometers of area. We see equivalent things in the UK. You can see that it weathers very easily, so we won't find a pristine, unconsolidated tuff in the UK. And what we find actually is what's deposited from this weathering. So here's an example from the Lake District. This is some Honister green slate. So this is andesitic material that was a big ashfall, probably into water, and then it was reworked so it didn't weld because it was cooled down by the water as it fell and as it settled through the water, which then meant that there was ash-sized particles, sand and finer particles that were reworked by the currents in the water. And so you get things like this, some nice graded bedding running through here. These little strange shaped, almost mini pillows up here. These are soft sediment deformation features where the denser sands have been sitting on top of the less dense clays, and so the clays start to push their way up through, and you get this little density inversion that's running through here. So these are strong evidence that it was all very soft sediment, as the name would suggest. So this is what something like the Fish Canyon tuff might end up looking like once it's all been reworked and deposited in a lake somewhere. You do get big ash deposits that land. They're still hot when they land. They're called pyroclastic. So that means glowing blocks. They're hot enough to glow at night, so at least 500 degrees C. And now under those conditions, then what happens is that the rock welds together and makes a very, very strong rock. So this is in Glencoe. This is the end of Glyder, and you can see in the bottom, so basically up to where the trees go here, where the dark rock is, this is andesite. And then there's another eruption on top of this where the steep cliffs are. This is rhyolite. And the rhyolite cliffs here are all welded, so they were very, very strong. They turned into solid rock pretty much instantly that they were deposited. And in fact, we see things like fiamme here and rheomorphic textures, which are evidence the rock was still soft. It was hot enough to be soft when it landed, so it all welded together. Okay, and you can see discussions of fiamme and rheomorphic textures in some of my other videos. So this is a nice example of how granitic composition, extrusive rocks, so rhyolite ends up looking in the UK in ancient rocks. This is how basalts end up looking if they're extruded. So very low angle flows, and each one of these parallel table lines is an individual lava flow. Okay, so this is one of McLeod's tables on Sky, and each one of these is a basalt lava flow. So you can see basically flows have come out and flowed out, and then the next one stacked on top to build it up like this. And this is called a trap geography, TRAPP, and you get very, very large flood basalts which have these kinds of trap geometries. There's the Siberian traps and the Deccan traps in India, and the Deccan traps are thought to have contributed to the climate change events that ultimately killed the dinosaurs. Okay, so some really large things that do happen with these flood basalts. So we get really nice examples of this kind of thing in Skye and up around that west coast of Scotland. So if we look at where we see these, this is where we're just looking in Skye, and through Ardnamurchan, Rum and Mull we see a very nice basaltic volcanism, and the Giant's Causeway in Northern Ireland down here. For andesites, we see here andesites and rhyolites. We see these in the large calderas in Glencoe, the calderas that we see in the Lake District and in Snowdonia, and also andesitic. The north face of the Ben is andesitic as well. And then in terms of major igneous intrusions, then we're looking at granites down in Cornwall and up through the Grampian, so the Cairngorm granite and the other Grampian granites up here. So that's everything. Thank you for listening, and hopefully that will give you a conceptual framework for seeing igneous rocks when you're out in the mountains and understanding, are they intrusive, are they extrusive, what's the grain size, are they in dykes or other bounded formations which have country rock on either side of them, and then what's the style of eruption that's produced them. Was it a relatively gentle fire fountain and lava flow, or was it a very violent eruption